Alright, welcome back to another video. This time it's not a solve, but kind of just a demo and talk about maze lambdas, which have kind of come out recently, I guess, from Dim and Bo's videos. So I spent yesterday watching those, understanding them, and trying to make my own, so I thought I'd just go through some of what I did, because it might be interesting. So first of all, I guess I want to show a video demo of some of this. So this is kind of what inspired me to do this. So in this video, it's kind of a battle between the robots and Dim, and he demonstrates solving a circular reference maze map classic type question. This one was really hard because you have certain input directions. So if you watch, you'll see how he solves it here.
This is...
Surely that's not...
No,
oh my god!
And it's kind of magic, because all he's doing is he's highlighting a map, telling his Lambda where the start cell is, what the allowed directions are, and essentially it's just telling him how long it takes to get to the specified place. Now, one of the first complication with these types of things is you need to mark a map with what directions you're allowed and what is not allowed. First of all, I wanted to create a Lambda that did that. So let's take this map. This is almost there case from last year. The classic way to do it, so the question basically says that snakes can see you from 2 cells away. So the way I used to do this is to kind of copy the snake and then paste it here and do that a bunch of times. Now, when I've practiced this case before, there's been times where I've accidentally missed a snake or I've copied into the wrong location. And that means my map is not really blocked out. And after that, I would essentially say, okay, if the cell is the specified starting cell, right is 0. If it's a snake or a wall, give me an X. And if it's something else, just give me the minimum of all the cells around it plus 0. So let's just demonstrate that. So let's say this was the starting cell, it would say 0. Then most people would have seen this. If you're watching this video, you'd have the minimum of everything around it plus 1. And then as I drag that out, you'll see that it's kind of going to show me the distance to everywhere. Okay, so this is how you would do it before. You'd kind of paste this formula in to all the cells that you're allowed to walk on, and then you could pick any cell as a destination and say, okay, this cell is 6 steps away. So the first thing I wanted to do is to have an automated way to black out this map. Wouldn't it be nice if I could make a formula where all I do is highlight a map and give a table of all of my things that I can't walk on with a range. So let's say snakes have a range of 2 and the wall has a range of 1, which just is itself. So let's just format the painter here, and this is what the blocker does. So I say block out map, this is my map, and then my blockers are here. And what that will do is it will automatically block out all of the snakes and the wall, as you can see, and it ignores everything else. And then I can use this map to do my circular references and find the distance to everywhere, and I know I won't have made a mistake by copying something in the wrong place or trying to block out cells I shouldn't have. I can also increase the range of things. So I can increase the range of this brick wall to 2, and then this is blacked out. So that makes it quite flexible and nice, so I can kind of create maps for any situation. I also have an optional argument to change the fill to be anything I want. So the fill could be A, for example, and you'll see those X's will change to A. So let's just go through that Lambda quickly in my Lambda file. So this is the Lambda that I built, and it uses one of my old ones, which is closest on map, and other people have like neighbors of. So instead of going through this Lambda here, let's take it from first principles. So essentially what I'm doing is I'm checking each cell in my original map. So I've taken O13 as an example, which is down here, O13. What I've done is I've taken the row number of O13, it's the actual row number in the map. So in my Lambda, what I do is I take the row number of O13 and I minus off, the minimum row number of the map to get so that when I index the map, I have the right row number in the map, if that makes sense. So this is like 7 rows down, and it's 14 rows across in the map. Then I get my max distance. So I want to look for everything 3 cells around that, because it's the max distance that anything can see me from in my range. So here I'm saying these bears can see 3 cells around them, this bear can see 2, and water can see 1. In reality, the first step I should do is mark like water or anything, and I could do that with a formula to say if it's, you know, the animal that can walk on water, keep it blank, otherwise give an X, and then that would allow me to solve many situations. So let's just quickly say, put that as W, and you'll see in here all my water is now changed to an X because water is not allowed. So back to how the lambda's working. What I'm doing is for each cell I'm taking an index of kind of the max range away, 3. I'm minusing 1 off it because really I want to index 2 back, which would give me a distance of 3. And then I'm doing a colon and an index forward. So that's going to spill out a range. So from 013, which is this cell, I'm kind of doing this calculation, indexing on it, and then I'm doing a make array with, you know, the max of the row in make array minus my max distance and so on to get the distances. Then I am two-calling this, two-calling the distance, and I'm doing an XLOOKUP on my table to check the max site. Then I'm saying where the site is further than how far it is away, give me an X, and then I'm saying, in the lambda I'm saying, or any of those are X, put an X there. Any of those are true. So let's just look at the actual lambda. So this is kind of it from first principles. The only tricky bit is when you have bounds of a map. So if I'm starting in the first cell of the map and I try and index 3 cells back and 3 cells above, it's going to be an error because those cells don't exist. And when I try to do my make array, then the distances aren't going to line up with the bounded index that kind of pulls out. So hopefully that makes sense. So that's one of the tricky bits. Now I have my own lambda to check things that are closest on a map, and I've used that instead to overcome that limitation and not have to rebuild this whole thing from first principles. I've also changed my closest on map lambda to not use indirects, so it's a lot quicker. So what I'm saying here is I'm saying take a map, let the range be my closest on map lambda for the max of the second column of my range table, so check everything within 3 cells, and then the range of each item is kind of an XLOOKUP of all of the items in my closest on map lambda into the second column here. Then I'm saying whether you can see it, so if it's just this again, if the site is bigger than how far it is away, then that will give me true, and then this is just giving me my fill, so I'm saying if fill is omitted, give X, otherwise give me my fill character so I can determine the character. And then I'm just saying if there's anything that can see me, give me the fill item. So let's quickly now use the actual lambda instead. So block out map, this map, and this range, and I'll get exactly the same thing, of course. So where that comes in really useful is on cases like this. So a recent one that came out for FMWC UK, Elliot made this map, which is extremely visually impressive. It has a lot of icons, and we have, you know, Merlin can see 4 cells away, the king can see 2 cells away, and the trouble you have with this is you have to then find those symbols if you do it the old way. Okay, the crown's down here, but I only know that because, you know, I've done the case. Then you'd have to highlight and block that out on a map, and it gets really messy. So this just makes it a lot easier to, you know, mark out where things are without manual errors. And you can see this is a little bit slow. So I'm actually going to talk a little bit about calculation speed as well in a second. So here you can just see we've marked out the things that have a range there. Now in terms of calculation speed, when you use an indirect, which I used to for most of my lambdas to find differences between rows and columns, it's slow because they're volatile, meaning they recalculate every time you do something in a spreadsheet. So if you solve one question with indirect and then you do another question, it's going to recalculate all those old indirect formulas. If you don't use an indirect, it won't recalculate those, so it's fast, but if it's computationally intensive, it still might take a little bit of time by itself. So the first, I guess the first goal into making things faster is to not use indirect. So I've done that step. The next step is to make the formulas more efficient, but when it's really computationally intensive, there's only so far you can go with that. And then the third Third way to make them faster is to upgrade your hardware, so you get a more powerful CPU and PC. You have more cores in your CPU to split the calculations up and do everything. My PC is quite old, which is why this takes a while, but now I've got rid of the indirect formulas. When I upgrade my PC, this should become very fast. I think indirects also force calculations to be on like a single lane and a single core in the CPU. I've read that somewhere, rather than optimizing all the cores on your CPU, so that slows you down a lot. So getting rid of the indirects is really crucial for calculation speed. So that's the block out map. Okay, so now let's talk about the maze lambdas. Bo has a video, which is I think where most of this stuff stemmed from, and it's this video here, move along available path without circular reference. And what he does is he creates and shows you all the steps to make a formula, a lambda, that will do all this circular reference stuff and calculate distances on a maze without circular references. So I have amended his formula to fit kind of my style, and this is the lambda. So I'm just going to kind of go through how it works. So when Bo originally did his video, he marked all of the available areas with a 1. And what I wanted to do is I wanted to mark out blocked areas and then have the lambda work off that. So I'm not going to explain this very well, but I'll try my best. So each cell in a grid can have a coordinate, right? An x coordinate and a y coordinate. So 1, 1 might be cell A1. So let's just open a new tab here, A1. So that could be worth 1, 1. Let's say you wanted to move down a row, you could have 2, 1. And if you were to add these together, you'd get a single number. So this would be 2, this would be 3. Here you would have 1, 2, so row 1, column 2. But the problem is, if you wanted to have these unique, then these two are the same, right? They add to 3. So a really clever way to get cells unique is to make the rows worth 1 times a constant, so let's say 1,000. In practice, Dim, Bo, and myself now are going to use 1,000,000 because it allows you a much wider range before you ever hit that issue where you run into a duplicate value. So let's say you had 1,001, this would then be 2,001, this would be 1,002. And now if you add these numbers up, you get unique numbers that specify a row and column. The good thing about this is you can also add directions. So if I move down a cell, then I just need to add 1,000 to wherever I was before, and that will give me a new cell. That's some of the fundamentals behind this lambda. So here are the places you can move, and here are, what you would need to add to your existing value to get the new cell coordinates. So you add this, and that will tell you what your new coordinate is according to this naming scheme. So I watched Bo's video and recreated his lambda, and then I kind of went through and understood it really well and made it my own to fit my style and the way I do things. I never normally use this movement convention, but you kind of can't escape it here in the way this works. Let's try and break this down. We are specifying an input set of directions here, which are just these arrows, and then I have this optional, so no diagonal. So all I'm saying is if there's no diagonal, so it's 0, then take only the first 4 of these, which is the up, down, left, right. Otherwise, take the whole lot. And then what we are doing is we are saying, first of all, RCN, which is here, is giving me the row column numbers of the map in that naming convention. So for this map here, B2 is going to be 2,000,002 because I'm in the second column, second row. And then we're in the third column, second row, so we get 3,000,002 and so on. So each of these will have a unique number assigned to it. Then this big reduce here is basically, let's just show you it, RS. It's kind of a reduce which is running off of this sequence, and I've made it rows of the map times columns of the map, which is a number that iterates for the number of cells on a map. So essentially, I'm never gonna run out of iterations before I've calculated everything. So if I could move along a whole map, then I'll calculate that. So let's just do a sequence of 1. So that's just going to give me where I can move within 1 space. And what that is doing is it's basically taking my first coordinate, it's adding all the directions, which is this bit, and then it's saying look up that in the map, in a 2 column of the map, and then if it is an X, I've also added an optional block here. So if I didn't want to use X, I could use something else, which I'll show you in the lambda. So if it's an X, then filter it out and also filter out anywhere you've been before. and it's starting from, so the reduce is starting from here and h stacked with 0. So it's taking this, you'll see the start is h stack, this and 0. So that's kind of saying we're 0 steps away. And then when we iterate through this lambda, we're v stacking all of the possible places we can go and this 0 plus 1. So here is that plus 1 in the lambda here, this plus 1. In Bo's video, because he uses 1 as everywhere he can go, he pluses c, which is a variable for that 1, which obviously wouldn't work. He also puts the start cell, the convention he uses that the map will work from this position and it will also work from this position, but if the map was further down the page it wouldn't work. I think that was just an oversight in his video, but I had to correct for that. So let's go back. So we then iterate through everything here and we have a list of the cell address and how many steps it is. And then essentially what we're doing is we're looking up all of these that are spilled across here in that table and returning here if it's valid. Otherwise, we are giving a blank. So here's that blank. So we're looking up RCN in our RS table. This is our RS table. So let's go end again. So I probably didn't explain that very well, but this is very complicated. Go watch Bo's video, make it yourself, try to understand it, and I think you know you'll be able to get there like I did. So I've since looked at Bo's Lambda file, and he has a better version which is quicker, that doesn't use a reduce, it uses an iterative lambda. I don't understand how that works, so I didn't use it. I tried to understand it, but it's far beyond me. But the thing I like about that is he has this target cell. So if you put the target in, you can add an end cell. So let's say the target was this top water cell, so it's 49, which in our original map is C4. If I was to just put C4 in here as the target, I should just get 49. Oh, I need to change this to final. Sorry, I didn't label the final argument of my lambda. So if I specify a target, this C4 cell, then it will just, all I'm doing with my target part of the lambda is I'm saying, if there's not a target, just give me the full map. Otherwise, look up my target coordinates in that RS table. I'll just show you that again, which is giving me all the coordinates, how far they are away, and return the second column, which is the number, so it will return 49. Equally, let's look at this one. This is 47, so if I was to return F3 as my target, and generally in map cases, you would put a target in because it's going to tell you where the end cell is, or you would determine your end cell. Another argument I wanted to put in is, so I've got this no diagonal here. So if I was to put a, I've already got it on actually, 1 is no diagonal, without it is diagonal. So here we can see these 3 cells, you know, I can move diagonally. If I change the lambda to have a 1 there, it restricts diagonals. And the way it does that is it only takes the first 4 of these directions to add on each time. And I also have this custom directions argument. So the whole way this lambda is working is it's taking my start cell, adding all these directions, determining if they're valid, and then if they are, v-stacking it under with 1 more step. So in theory, I can put in whatever directions I like. So let's say I could only move 2 steps at a time. Well, then this would be 2, this would be 2, this would be 2, and this would be -2. So I could actually just put in my specified coordinates, so these custom directions. So let's put that at the end. There's my custom directions. So now I've put in my custom directions, but only left, right, up, down. We can see that we can go 2, that's 2, 3, 4, 5, 6, because we're jumping 2 steps at a time. So on this, we're not in Kansas anymore. There's a question that asks how long it takes you to get to a specified cell. So what you could do is you could use this lambda and give it a start cell and put in the direction movements, which is all the diagonals, you know, if this was the start cell, or it's 2 cells across and 2 cells back. So for that case, you know, I could just give it new directions and it would all work. So that's probably a terrible explanation, but hopefully it somewhat makes sense. Let's just get myself back to a good position. So now let's have a look at it in action here, just with the lambda and not the full text. So first of all, I just say maze here, and my start cell was actually back here. Let's put the start cell here, E13, and let's do that. So I could change this start cell to be, I don't know, V14. V14, and then we see V14 as start cell. I can also open the canals here. So in this case, these were canals, and they opened for certain types of ships. So I could have this as my map, use a data table, and say, you know, if the ship is small, then this is blank, otherwise it's an X. And then I can turn that off, and it will work, and it will open that canal, as you can see here. I can also, the next argument I've got is, you know, whether to restrict diagonals. So let's say restrict diagonals. That will change all the distances. Then I have block. So if my block was actually a different letter, A, for example, then this all opens up. And let's say I was to put an A here. Now we can see that area of the map is blocked out. The reason I have that blocker in is because I might have a map that I don't have to manipulate and block anything out, and it just says you can't walk on any blue cells. So all I do is change the blue cells to W, and then I can put a W in here. Or if X was already a character on the map that was needed, it allows me that flexibility. Target obviously is, like I explained earlier, just pick out one of these numbers for a given cell, and then custom directions are custom directions, which I've been through already. So let's now try this in action, which I've only done on a couple of cases, but I want to try it on a few harder ones to see what happens. So in this case, for example, right at the start, I showed you me blocking out the map here. So let's paste this into a new, so let's just paste this over here as values, I guess. And then on the case, we should be able to just say maze. This is our map here. Our start cell is here. We can move diagonally, so I don't need anything for that. The blockers is an X, which is the default. I don't have anything different blocking me, and the target is this. And that should give me the value 8. So I'd need to lock that map before I was to drag it down at all, and then let's just copy that into another random cell to see if it works, and it does. So that's that case shown off. What other map cases do we have? Let's try Bear Island, the classic case. So we want to make a new map. Let's copy that, and we want to set up a table of what we are not allowed. So we already have that here in the instructions. So we also have water with a range of 1. These actually need to go up by 1. Whoops, 3, and they have a range of 2. Let's make the water be flagged as water. And then we're going to say, I need my lambdas in. So block out map. Here's my map, and here's my table, and then on the case we want to go from the plane, I think, and determine how long it takes. So where's the plane? It's in E27. So maze, the map is here, our start is E27. Let's lock the map, and we can move diagonally, and our target is this. Okay, that seems to work nicely. As you can see, it's a bit slow, but it's not too bad, and that slowness is due to my PC, not because it's using indirects or anything. I think there was a bonus question about this as well, which was what's the longest minutes it could take. So okay, all I need to do is say equals maze. This map start was E27. And then I should be able to just take the max of those. Unless it does something funny with blanks, which is 31. So is that right? Yes, it is. Okay, so it's working as intended. Now the real test will be probably the case that we had, I'm Just Wild About Harry, because that was really hard and you had specified directions. I've not tested this yet, so this is very much a live test. So I need to remind myself of this one a little bit. Let's have a look at the map. Okay, so that's here. And actually there's no blockers here other than the water, I think. So let's do it with a data table. So I think I needed to figure out what cell the banana was in. I'm going to put some headings in. I haven't done this case since it came out, so let's just figure this out kind of live. Okay, and flatten this map. Start is going to be here. First end is going to be look for the banana in our flattened map. Next start is going to be there. End is going to be there. Okay, so first of all we're going to need a flag on the water. So let's just do that. Here can be water. Okay, good. And then let's do our map. So M, let's just copy this for now. And blank everything out. If it's not Howard and it's water, do that, otherwise do blank. And then we should have our open map, and let's just change this to Howard. So which one has Howard? Number 101. So let's just try 101. We should get our map, oh, no, sorry, 102. Should get our map fully then opening up, which we do. So let's go back to example 7. So let's say equals maze. We have this, oh, we need our input directions as well. So let's do equals x lookup person in the case. Give me directions. And let's split those down. Okay, so let's say equals maze. We have this as our map. Our start cell is here. Just gonna lock these. Diagonals doesn't matter because I'm gonna put in custom directions. My block is an X, my target is that. My custom directions is arrows to reference. I have a lambda for that of those. We should get a distance out. And let's just lock these. F4. This is where I need a new PC. And then here we should have the distances there. 29, so that gives us 80. Does that match the example? Yes, it does. Let's just try it for one more question number. So let's try one with Howard, 109. Let's give that a go. 109. It's quite intensive. We should have 46. So let's try that, 46, and it works. Okay, good. So, I mean, this feels like a bit of a cheat in a way, but my view on lambdas is, when I was a beginner, which wasn't long ago, a year and 4 months ago, you know, I didn't know any of this stuff. I didn't know the circular references. I went down the path of trying, you know, Bear Island, which was a free case, and couldn't do it, really wanted to know how to do it, so I watched a video and was like, wow, that circular references is really clever. Then as I progressed over the months, I started to understand lambdas and things I didn't know about Excel, and that's the whole point of, you know, doing the championships is you level up, or at least that's why I wanted to do it. And I learned loads of stuff, and I started to build my own lambdas, which helped me compete. I don't think banning lambdas helps the competition really. And part of the reason I think that is because it stifles, if you ban them, it stifles progress. So the only reason a lot of people make these lambdas, they may spend weeks on them, certainly I have before, to build something clever to solve certain tasks in the Excel World Championship, and then the community shares all those out like I have here, so it doesn't really put people at a disadvantage because we're sharing this stuff, and in doing so, we then push the boundary of what Excel is capable of. So I built that closest on map lambda, and then I've used that closest on map lambda to build this blockout map lambda, and they build on each other and allow us to do things that we'd never have got to or never have got to understand if lambdas were banned. We just wouldn't push that boundary of Excel, in my opinion. So anyway, that's it for this video. It was a bit all over the place, and I haven't really, this isn't a planned video, this is just kind of a talk, I guess, a showcase. So hopefully it was interesting if you made it this far, and I'll see you next time for the next round.